Okay.
I actually really.
And so right now we've got our data folder from 2019-05-23. We're going to spec no background. And we've got a series of different files, htxs_xps_be_xas and no background. For this particular training, we want to have our XAS data set. For the Windows users, just click on it. If you're a Mac user, then you have to actually select it out of an already open PyMCA file. You can see PyMCA right there. And we hit OK. And our executable should begin. And all we need to do is just go ahead and click on our first data point. And we should all be on this same page. I always like to click and drag and open up the command a little bit more so you can see more of the name and kind of make the space a little bit easier to use. So you've got your data window, file window, and then where all of the counters are. And in this particular case, remember, we don't want to just plot TEY. We want to plot TEY divided by I0, which is right there. And Igor can be a little PyMCA can be a little fidgety. Most of the time it should actually update and say TEY divided by I0. You'll notice in this particular case that it's not doing that. I0 is the current that's coming off of a small piece of metal, piece of gold that's in the beam path. Why do we do this? Because we want to normalize to the beam flux as a function of energy. So we've got a whole series of different pieces of data. Right now it's on auto add. Get rid of auto add, guys, and go ahead and do auto replace. Go from auto add to auto replace. If you're in auto add, as you click multiple files, it keeps stacking them up and things just get real hectic real fast. We don't want that. We want to have more control and just have single scans. But if we want to use auto replace and still put in multiple pieces of data, we can do that real easy by just clicking and dragging. So one of the main things that we want to highlight is the fact of the naming nomenclature that we use. And so here it is, scan 66. We've got XC1S, so X-ray carbon 1S spectroscopy. D55, that's our magic angle. Z1 is giving us some information about our sample position in Z. And then S3 is our sample name that we gave the particular samples. And we need to keep the name short because we ended up having issues if we go over 31 characters in Igor. So everybody should print up the shared SSRL run that we used on May 23rd, and then you can get an idea of what the sample names actually mean. So S366, if we go back to our key, S3 is ND-OX500C acid base. One thing that you want to recognize is that it's a short scan. This is our quick scan that we use at the beginning to determine whether or not we're at a good spot on the sample surface. And the x-axis is just 285 to 320, and the number of points is only 52. We don't want to actually spend any time now, because we collected this data at the beamline and it was only for optimization purposes. So what I want you all to do is to click and drag until we get away from the 52s, points 52, points 52, until we see 364. When we see the number of points is 364, that's our high-res scans.
I am not even yet able to get to the folder, honestly.
No? Okay, let me pause here. For today's work, I think we should really focus on the carbon and the boron scans, since we've got Team Boron in the house. And that includes a whole series of scans which are starting at S39, I believe. So let's go down and let's identify where our S39 begins. So let's see, S38. That's BCL3, 3 hours, 321.19. Let's get to that guy.
And that is in the first set of boron scans, right?
Yeah, and that's the first set of boron scans, scan 485. So that's our high res carbon scan.
Carbon scan.
This is a carbon scan.
485.
And we can go ahead and start doing some combination of looking at boron, carbon, and oxygen all at the same time.
Okay.
And we can do that really easily by finding the oxygen for S38 and boron for S38. And the reason this is important is that we are doing soft X-ray spectroscopy. We are exciting 1s core level electrons to unoccupied anti-bonding orbitals. The photon energy that we use during these experiments are directly related to the attraction of the electrons or negatively charged particles with the positively charged nucleus. So let's go ahead and scroll down, and this is kind of the beauty of PyMCA. Let's go ahead and just scroll down until we find our oxygen scans.
So get one oxygen, one
Oxygen 1.
carbon, and one boron.
Yep. And so it's XO1S, and that's how you know that you're now in your oxygen scans. We want to go ahead and do S38, so I'm going to click on S38. And you'll notice now that not only do we have carbon, but now we've got oxygen as well. And it's this continuation. We could go ahead and put in nitrogen too. I don't think we did it as a control for S38, I don't believe. Maybe we did.
That's what it looks like.
Oh, interesting. So, we've got that in there as well.
It's in there somewhere.
Yeah, I don't see it.
I selected it, so I hope
I'm not seeing it, but that's okay. I can just put in, I'll just put in S50 as a holder in there.
nitrogen we didn't do. No.
And then I'll go down, and then let's find our boron. So B, XB1S, S38, and she's right there. That's scan 696. And this is kind of the beauty of it. Like, you're watching all of these transitions of these electrons in energy space. So remember, on our x-axis is the photon energy.
Mm-hmm.
As we go across the periodic table, where we are looking at these transitions based on the Coulombic interaction between our negatively charged particles, our electrons, and the nucleus. So we've got boron, carbon, nitrogen, oxygen, and just for fun, let's go ahead and find a fluorine scan. Fluorine is scan 735. So let's put 735 in there as well. And so when you were in general chemistry, they might have told you, oh, this is this periodic trend that we see for atomic radii and electronegativity and all of these other things. Well, this is the real example of the stability of those core level electrons in the nucleus. And you'll notice that on the left-hand side, we've got 200 eV photons up to 700. And if we looked at the periodic table at the same time, we'd be going through Z equals 5, Z equals 6, Z equals 7, Z equals 8, Z equals 9. So right through everything. So it's quite powerful. So now let's go ahead and just click and drag around our boron scan. I forgot which one it was, But let's just go ahead and click and drag around it and zoom in on that daddy. And it looks like we've got a beautiful peak for S38. Very nice peak for S38. And this is our BCL3 for 3 hours. What I'm surprised to see on this one is the fact that we've got information for diamond. So if we were to click and drag around diamond, we've got most of the telltale signs that we would expect for a regular diamond sample. So please go to the options, guys. Go to options, toggle crosshair. And if it does this to you, don't fret. Just take the crosshairs out and bring it back.
Alright,
So if it goes wonky on you, just remove and bring it back. Now on these experiments, we are off by 1.3 EV. And we'll use an X shift in Igor to correct for those errors. So that is not a big deal. Remember, the core hole exciton for diamond should be at 289.0 EV. We observe at 287.7. The second absolute band gap in diamond should be at 302.0, and we're off a little bit as expected. Okay. So if we're looking at this carbon 1s spectra, I think what's really neat is we should click and drag around this area so that we've got the core hole exciton and a lot of these pre-edge features. Now, one of the reasons I drew up on the board is that we might have a sigma star BCL or maybe a sigma star boron carbon bond is right here. Now this is a feature that I have not seen before. So this is our core hole exciton. You'll notice once again, this is kind of it's like a calibration. And the calibration is actually within the sample itself. So that's how we know that the energy calibration isn't good, because it's not at 289.0 EV, which is where it should be. So when we see this feature that's in the pre-edge right there, and that looks like that is 287.1, well, that's actually at 287.1 plus 1.3 EV. So that would actually be 288.4 EV. We typically don't see any features there. This is new to us. You'll also notice that there's a shoulder here at 286, but that's really 287.3 EV. And then we've got another feature that's at 285.13, which would actually be 286.4. So we've never successfully synthesized these samples. We've never actually gotten this type of information before. So this is our new way of examining them. And so we're going to have to basically dive into the literature for boron 1s related work. And if there's nothing good out there, well then, that's good for us, because then we'll be able to be in more high impact journals. So imagine now that these three features, here, 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 and here, are just like what we put up on the board. Those have a signal because some transition has occurred. Why? Because there is a bond there which should go ahead and correlate with a carbon-oxygen bond, carbon-boron bond, or maybe something else. And this is important. Remember, this is only carbon. So we are only probing the type of bonding environment around the carbon atoms. And since everything else in our system is diamond below, these are only those carbon-related bonds that are happening at the surface and above. Yeah.
Question.
Mm-hmm.
So if we're looking, for example, at like a carbon scan of boron, or where we identify there to be a peak that is associated with a carbon-boron bond, would we see a same or similar peak on a boron scan in the carbon area? You see what I'm saying? Like, do they correlate back?
They should. Okay. They should, yeah. And so let's go ahead and right-click out on our mouse to get back to where we should be here. So this is the good thing, that everything is still clicked. So don't touch any of the stuff over on the left-hand side, just the ones that we originally put in for fluorine and everything. And we can go ahead and click and drag back around our boron. Now, if our story is correct, if our analysis is correct, then we should have a consummate boron-carbon bond that's somewhere in this region. Right now, the thing is we don't know what we're looking at. That's kind of the beauty of the whole thing, is that we've got a series of different beautiful peaks at 188, 188.6. We've got our strongest peak at 190.2, and we've got another peak here at 191.43, and then another one as well. So we've got what appears to be 1, 2, 3, 4, 5 individual peaks, which probably represent carbon-boron, boron-chlorine, boron-oxygen related bonds that would be there. And these would still be representative of those same anti-bonding orbitals that we described for carbon. So the boron 1s electrons have now made a transition to some anti-bonding orbital. Okay, so we kind of come back to our boron scan right here. Well, overall, we've got these features which should go ahead and correlate to the bonding environment. And as you kind of get closer and closer, you'll actually see that I think my estimate of 5 peaks is wrong. And this is what we would do in Igor. We'd probably have to fit these guys and understand what the features are. But we see a peak right here, here, here. And if you zoom in right here, you kind of didn't see it previously, but this has a shoulder as well. So that's got a shoulder. There's another peak, and then the other shoulder. So there's basically a total of 6 individual peaks that we would need to identify and properly assign. Yeah. And Daniel, to your point, if we go ahead and we keep zooming out, and this is our oxygen-related peaks, well, this should then be related to only the bonding environments around oxygen. That's kind of the beauty of these techniques, is they're element specific. Carbon, boron is individually probed, fluorine is individually probed, carbon is individually probed. Typically, the feature that we have right here, that should be some sort of C double bond O related feature.
How do you unzoom, sorry?
Right click. Right click. You keep right clicking and you zoom out till you get to the original. Yep. Now, we could go ahead and compare and contrast to, let's say, for instance, S1. So if we were in our oxygen scans and we go back up, and remember, we would want to hit Control-click or we lose all of our information from all of our other scans that are on there. So we would go Control-click 568. Control-click 568. You'll notice that guy gets populated. It's got more counts probably because there's more material in there for one rather than the other. But we can click and drag around those guys, and you'll notice that the overall features look fairly similar. And you've got a peak at around 535 and then another at 540. And we can probably do a little bit of analysis to see the difference between the two samples. Overall, I would assume that any of the oxygen that might be on there could still be related to the unreacted carbon-oxygen bonds on the surface, the acids that might be on the surface, as well as maybe even adsorbed water. You know, we always want to say that our samples are dry, but we know that's not in fact the case. And if we've got some amount of adsorbed water, we should see it. Its only signature would be through oxygen. Yeah.
Right, because hydrogen is not enough.
Yeah, because hydrogen we don't see. Now we can see carbon-hydrogen bonds. We can see boron-hydrogen bonds or nitrogen-hydrogen bonds, but we cannot directly probe hydrogen.
Right.
Yeah.
All of the elements that are in that first row that can bond with it. That's
Yep, that's correct. And so once we're here, we can now go ahead and say, hey, we've got some good data, and let's go ahead and bring it into
Igor.
Igor.